Have you ever wondered how social media suggests new friends? Or how Google Maps finds the fastest route? Or even how scientists are discovering new medicines faster than ever before? What if I told you there's a powerful, really fascinating technology behind all of this? Something designed specifically to understand the relationships between things, not just the things themselves. Today, we're diving deep into a rapidly evolving area of artificial intelligence. Graph neural networks, GNNs for short. And here's the best part. This deep dive, well, it's designed to be accessible, crystal clear, even if you've never touched AI or wrestled with complex networks before. Our mission is to demystify GNNs. We want to show you what they are, how they work, and the incredible real-world problems they're solving, all with clear examples, analogies. Our aim is really to unpack GNNs in a way that helps you connect the dots, maybe even spark a few aha moments about how this seemingly complex AI actually works.
It really is remarkable how GNNs are, well, catching fire right now. Their unique flexibility in modeling complex, interconnected relationships. That's the kind of thing traditional neural networks really struggle with.
Right.
And that's what sets them apart. This field has just exploded from theory to practical, game-changing applications in just a few short years. So we'll start with the very basics. What is a graph anyway? Then we'll journey through the core idea, this message-passing concept that makes GNNs so unique. And finally, we'll explore how they're being applied across all sorts of exciting domains.
Okay, sounds good. Let's unpack this. Starting with something super familiar. Think about your social network. And I don't just mean like Facebook or Instagram. Your real-life friends, family, colleagues. You're connected to them, right?
Yeah.
And they're connected to others. Or think about a subway map. Each station, it's connected by lines to other stations. These are perfect examples of what we call graphs in the GNN world. So in any graph, there are two fundamental components. First up, nodes. Sometimes people call them vertices. These are just the individual things, the entities in your network. In that social network example, you are a node. Your friends are nodes. On the subway map, each station is a node, family tree. Each person is a node. They're the individual players, basically, each with their own characteristics. Then you have the edges, or links. These are the connections, the relationships between those nodes. So in your social network, a friendship is an edge. On the subway map, the track between two stations, that's an edge. Family tree, a parent-child relationship or sibling, that's an edge. And just like real-world relationships, some edges are directional, meaning the connection goes one way, like following someone on Twitter, maybe. Or a citation from one paper to another. Others are undirected, like a mutual friendship. The connection goes both ways. There's actually a great real-world example. The Jazz Musicians Network. It contains 198 musicians.
Yeah.
Those are the nodes. And get this, 2,742 collaborations, which are the edges.
Wow, that's a lot of connections.
Exactly. And what's fascinating is you can actually see these hidden communities of musicians emerge from the graph. It shows how they have strong relationships within certain groups and sometimes, surprising connections outside them. It perfectly illustrates how these connections reveal patterns you just never spot looking at the individuals alone.
Yeah, and that really highlights why graphs are so fundamentally important for AI right now. Traditional AI models, they're amazing when data fits into neat, regular structure, like images, right? They're essentially grids of pixels.
Right.
Or text, a sequence of words.
Right. Very orderly.
But the real world is just messy. It's interconnected. Data often exists in what we call non-Euclidean space, which sounds intimidating, I know.
It does a bit.
But really, it just means the relationships between the data points are more important than, say, their physical coordinates. Imagine a spider web. The strength and pattern of the connections are key, not just where each strand happens to sit on a flat surface. Graphs are just an excellent way to represent and process these inherently interconnected data sets. They let us capture the structure where the connections are just as important as the individual data points. And this ability to surface these latent structures, these hidden patterns, that's where the real power lies, revealing communities or surprising links you wouldn't otherwise see.
That makes so much sense. Okay, so we've got the graph part down, nodes, edges, connections. But where does the neural network part come in? For anyone new to AI, maybe we could do a quick recap. A traditional neural network, it's like a very smart data processor, right?
Or a decision maker.
Exactly. Think of it like that.
You feed it an input, let's say an image of a cat. It processes that through several layers of neurons, which are basically just little mathematical functions. Tiny decision makers, yeah, or switches. Taking inputs, doing a calculation, passing information on.
Right, and eventually it gives you an output like, yep, there's a cat.
Mm.
And it learns this by looking at tons and tons of examples and just subtly adjusting its internal settings.
Tuning itself.
But the challenge, as you mentioned, is that Traditional neural networks assume data has that very structured, fixed format, that image grid, that clean sequence of words. They really struggle when the relationships are irregular, dynamic, and, well, fundamental to the meaning, which is exactly what graphs are all about.
Precisely, which raises the big question, how do we get neural networks to work with these fluid, interconnected graph structures? And this is where GNNs get their magic. It's through a core process called message passing.
Message passing, okay.
Think of it like a rumor spreading through a neighborhood. Each person that's a node talks to their friends, their immediate neighbors. They gather all the gossip, combine it with their own thoughts, maybe their own information, and then they update their understanding of the rumor, this new updated understanding. That then becomes the gossip they share with their friends in the next round.
Ah, I see. It's like a cycle.
Exactly. That's essentially message passing. We can break it down into two key steps. First, there's aggregation, gathering. Each node gathers information or messages from its immediate neighbors. This isn't just, say, their features, but also their current understanding or even info about the connections themselves.
So if I'm a node, I'm listening to all my direct friends.
Pretty much. You're gathering what they know. And there are common ways a GNN aggregates this. It might sum it up, average it, maybe take the maximum value from the neighbors. Summation is actually used quite often. It gives a good balance.
Okay, summing, averaging, gathering info, what's next?
Second step is update. After gathering all that aggregated information, each node then updates its own information. It combines what it learned from its neighbors with its own previous state, its own information. And this new, richer information becomes the node's updated representation or embedding.
Embedding, okay.
Think of these node embeddings as like unique digital fingerprints, a rich, compressed summary of all the relevant info about that node and its connections. It helps the GNN understand its role or personality in the whole network.
A digital fingerprint, I like that.
And this whole process, gathering and updating, it happens in layers or rounds.
Right.
In each layer that follows, information propagates further across the graph. So after one layer, a node knows about its immediate neighbors.
Right.
After two layers, it knows about its neighbors' neighbors, and so on.
Okay. So the information spreads out.
Exactly. It allows information to spread across the entire network, even reaching nodes that are far apart initially. The real breakthrough here is that GNNs let neural networks learn directly from the connections, the relationships within that graph data.
That rumor spreading analogy really clicks. But if information is propagating in these layers, does that mean there's a limit? Like, can a GNN eventually see relationships across the whole network, even between nodes that are really far apart? Or does it mostly just understand its immediate neighborhood?
That's a fantastic question. Really gets to a core point. And you're right. In a single layer, a node only sees its direct neighbors. But because the process happens in multiple layers,
Okay.
information does indeed propagate further and further out. So after, say, 3 layers, a node has effectively incorporated information from nodes 3 hops away in the network.
3 steps away. Got it.
So yes, GNNs can absolutely learn about these longer-range relationships, even though the core operation itself is local, neighbor to neighbor. The challenge then becomes, well, how many layers are optimal? Too many layers, and the information can get a bit diluted, or the network gets too complex. Finding that balance is key.
Got it. So it's like a chain reaction, building up understanding layer by layer.
Yeah.
Okay, so we've talked about the what graphs, nodes, edges, and the how, this message passing idea. Now let's see these GNNs in action. Let's talk real-world examples. This is where it gets really interesting.
Exactly. And it's truly remarkable, the diversity of areas where GNNs are being applied now. We're talking crucial systems like fraud detection, recommendation engines, but also brand new frontiers, antibacterial discovery, advanced physics simulations. Their versatility is really impressive.
Okay, let's start with something many of us use every day, social networks. Think about platforms like Pinterest or LinkedIn. They use GNNs all the time. For friend recommendations, suggesting content you might like, identifying communities. If you're looking for new connections, a GNN analyzes your existing friends, the nodes and their connections, the edges to suggest people you might know. Pinterest, for instance, apparently uses GNNs on networks with billions of nodes and edges.
Billions. That's huge scale.
Right, to make recommendations. And it dramatically improves user engagement because it surfaces content people are genuinely interested in. LinkedIn uses them, too, to understand those complex relationships between people, skills, job titles, their professional networks.
And building on that, GNNs also power recommendation systems beyond just social links. Think about personalized recommendations on e-commerce sites like Alibaba or for movies and music on streaming platforms.
Yeah, though you might also like stuff.
Exactly. By modeling users and products as nodes and their interactions, purchases, views, likes as edges, GNNs can predict what you might like. And it's not just based on what you specifically liked before, it finds patterns based on what similar users liked or what products often get bought together. It's all about finding those subtle, interconnected preferences that aren't obvious on the surface.
Okay, and you mentioned drug discovery and chemistry. This sounds mind-blowing. Molecules as graphs.
It's incredibly intuitive when you think about it. Molecules are naturally graphed.
Atoms are the nodes.
Exactly. Atoms are nodes, and the chemical bonds between them are the edges. GNNs can learn directly from these molecular graphs. They can predict crucial properties of new molecules, like will this compound smell pungent, think garlic or peppermint? Or, much more importantly, will it bind to a specific protein receptor involved in a disease?
Wow, so it's predicting function based on structure.
Precisely. And this capability allows researchers to digitally screen vast numbers of potential drug candidates before they even need to synthesize them in a lab.
So it speeds things up massively.
Absolutely. We are talking about seriously reducing the time and cost involved, potentially shaving years off development cycles, getting new treatments to patients faster. It's a huge shift from the old, painstaking trial and error methods. Real molecules like allyl alcohol or piperitone, their properties can be predicted this way. It's happening now.
That is truly transformative.
Yeah.
Okay, shifting gears a bit. What if something really dynamic, like traffic?
Right. Another great application area is traffic prediction and route optimization. Think Google Maps, Waze, other smart transport systems. Traffic networks can be modeled as graphs. Sensors or intersections are the nodes.
And the roads are the edges.
You got it. Roads are edges. GNNs can then predict things like traffic speed, volume, density. They do this by understanding the relationships between different road segments, how congestion in one area impacts another.
Yeah, the ripple effect.
Exactly. And that helps optimize routes, logistics in real time, making commutes smoother, deliveries more efficient.
Okay, and finally, a huge one that impacts almost everyone. Fraud detection. Financial
Yeah.
fraud. It's a massive, constantly evolving challenge. Fraudsters create these complex, hidden patterns. Relationships between accounts, transactions, things traditional methods often miss because they just look at data points in isolation.
Mm-hmm. GNNs really shine here.
How do they actually spot what the old systems miss?
Well, it's really about seeing the network. In credit card fraud, for instance, you can think of transactions, accounts, cards, devices. They can all be nodes.
Okay.
The edges then show the relationships, maybe the same card used in multiple places quickly, or several accounts linked to the same IP address or device. GNNs can identify suspicious patterns by finding a structural outlier.
Structural outliers.
Yeah, like a tight cluster of highly connected accounts that might form a fraud ring. The structure itself looks suspicious. Or they can spot contextual outliers, where a seemingly normal account makes a transaction that's just highly unusual given its connections to other entities.
Ah, okay. So it's out of character for that part of the network.
Exactly. Companies like Amazon were using GNNs for this way back in 2017. Adyen built a specific system treating sellers as nodes, their connections as edges, to classify fraudulent sellers. And the results. GNNs have been shown to outperform existing business rules and models by a big margin in catching sophisticated fraud because they see the network of fraud, not just individual flags.
Seeing the whole network, that seems key.
It really is. So how do these GNNs actually learn to do all this? How do they acquire these remarkable capabilities? Well, just like perfecting a recipe, GNNs learn through a process called training. You give the GNN a large data set of graphs where you already know the outcomes. So a collection of molecules where you know their smell, for instance, or financial transactions already labeled as fraudulent or legitimate.
Okay, so you feed it examples with the answers.
Right. The GNN then makes a prediction based on what it's learned so far. If its prediction is off, it gets feedback. We measure how far off it was using something called a loss function.
Like tasting the recipe and realizing it needs more salt.
Exactly like that. Based on that feedback, the GNN iteratively adjusts its internal settings, its parameters, or weights. It's essentially fine-tuning its own internal recipe for doing that message passing and aggregation we talked about.
Adjusting things bit by bit.
Yeah. And this process repeats over many, many cycles, epochs, or rounds until the GNN's predictions are as accurate as possible. It's this continuous refinement, learning from mistakes, that leads to those accurate insights into complex relationships. And what's fascinating is the versatility of what GNNs can predict. They work at different levels of the graph. First, There's node-level prediction, predicting something about a single node.
Like, is this account spam?
Exactly. Is this social media account a spammer? Does this jazz musician belong to a certain community? In fraud detection, it's classifying if a specific transaction or account, a single node, is fraudulent.
Okay. One node at a time.
Then there's edge-level prediction. Here, the GNN predicts something about the connection. Does an edge exist? Should it exist? What are its properties?
Like predicting friendships.
Perfect example, predicting future friendships on a social network, or identifying relationships between objects in an image. In finance, it could be predicting suspicious links between entities that might indicate a fraud ring, even if the entities themselves look okay individually.
Got it. Predicting the connections.
And finally, there's graph-level prediction. This is predicting a property of the entire graph as a whole.
Like the whole molecule example.
Exactly. Is this entire molecule toxic? Does it smell a certain way? Or maybe classifying an entire document based on the graph structure of its words. It's analogous to image classification, but for the whole graph structure. And maybe the most crucial benefit, what makes them so practical, is their ability to generalize. Generalize.
Yeah, generalized to new, unseen data. Once a GNN is trained, you can give it a completely new graph it's never encountered before, and it can still make accurate predictions about its nodes, its edges, or the entire structure.
Even if it hasn't seen that specific graph before.
Right, which is vital for the real world, where data is constantly changing and new patterns are always emerging.
That ability to generalize seems incredibly powerful.
Okay, so we've covered a lot of ground. We journeyed from the basics, nodes, and edges to that sophisticated message passing idea that lets GNNs learn from connections. And we've seen how these models are really transforming things. Social media, road optimization, drug discovery, and yeah, definitely fraud detection. It feels like GNNs help us uncover hidden structures, dynamics, and data that, well, traditional methods just can't really capture. They offer a shortcut, maybe, to being well-informed about complex systems by focusing on the relationships, not just the individual pieces.
That's a great way to put it. That ability to understand the intricate relationships is the game changer. And it's truly remarkable how far the field has come, but, it's still evolving very rapidly. While GNNs are incredibly powerful, they do face ongoing challenges.
Like what?
Well, for instance, most GNNs are relatively shallow, often just 2 or 3 layers deep. This means they mainly gather information from a somewhat limited neighborhood around each node. If you go too deep, make the network too many layers, you can run into issues. The node representations can become overly similar. It's called oversmoothing. Distinct nodes start looking alike to the network.
So deeper isn't always better.
Not necessarily, no. There's a balance. Another big challenge is scalability. Training GNNs on really large, constantly changing graphs that can be computationally very expensive. It presents real hurdles for putting them into production.
Makes sense. Big data means big compute.
Right. And then there are the real-world data issues. Things like imbalanced data. You mentioned fraud cases being rare, right? That's a classic example. Or noise in the data, maybe mislabeled information. And adapting to out-of-distribution scenarios.
Meaning patterns they've never seen during training.
Exactly. New types of fraud, maybe. Researchers are actively working on solutions for all this rebalancing data, handling noisy labels, improving generalization to these unseen situations. So, as GNNs continue to advance, you have to wonder, what new hidden connections, what new insights will they reveal next in the world around us? Think about the intricate networks just in your own life, your personal connections, the systems you interact with daily. Where else might understanding relationships, rather than just individual parts, unlock truly transformative solutions? What seemingly unrelated pieces of information out there might actually be deeply connected, just waiting for a GNN to reveal their secret? It's a fascinating thought.
It really is a great question to ponder. If this deep dive has sparked your curiosity, remember the world of graph-structured data is vast. There's always more to learn. Keep exploring.